Hi everyone, welcome back to Caroline's Chemistry. In today's video, we're diving into one of the most useful ideas in chemistry, concentration of solutions. We'll break down exactly what concentration means, the different units chemists use to measure it, and how to calculate concentrations from moles and volumes. Then we'll tackle the types of exam questions you're most likely to see and clear up the mistakes students often make so you don't fall into those traps. By the end, you'll feel confident handling concentration problems, whether it's for your GCSEs or as a foundation for A-level chemistry. Welcome, let's talk concentration. So let's start off with something that is very seriously misunderstood, and that is what is concentration. Again, I'm not just interested in you being able to use an equation. Like, what does each bit of this mean? Because that's how we get super good and don't make silly mistakes. So concentration is usually measuring in moles per decimeter cubed. Now, what does that actually mean? Because there's a lot of fancy words there. So moles, remember, is a number. I've done a whole nother video on what moles are. If that kind of confuses you, we can go into it to more depth. Look that video up in my channel. So moles is a number. It's a very, very big number. It's 6.022 times 10 to the 23, but it is a number of particles. A decimeter is a volume, so a set amount of space. So all concentration is saying is how many particles are in this set volume. And a set volume, 1 cubic decimeter, is the same as a litre. Think of those litres of pop or water that you might buy. That is what 1 cubic decimeter looks like. Now, let's see if we can understand this before we then again use the equation. So if we have that concentration is moles per decimeter cubed, let's take this example of, well, if we have 8 moles dissolved in 4 decimeter cubed, then what we need to work out is, well, how many moles are therefore in 1 decimeter cubed? So of those 8 moles, scale it down to 1 decimeter cubed, and 2 moles would fit in each 1 decimeter cubed. So that's our concentration. We have 2 moles per decimeter cubed. If I therefore have 4 decimeter cubed, I have 8 moles. Let's go in the reverse. So if we have 0.5 moles dissolved in 2 decimeter cubed, then again, I want to try and find out for concentration, how much is in 1 decimeter cubed? So half it. If there's 0.5 moles in 2 decimeter cubed, there must be 0.25 moles in 1 decimeter cubed. That's our concentration. Now, if we have a volume of 3 decimeter cubed and our concentration is 2 moles per decimeter cubed, what that means is for every decimeter cubed, there are 2 moles. For every 1 decimeter cubed, there are 2 moles. So if I have 3 decimeters cubed, I must have 2 and 2 and 2, so 6 moles of sodium chloride. And then finally, in this example, we have 0.5 decimeter cubed of a concentration of 0.4 moles per decimeter cubed. What does that mean? It means that in every 1 decimeter cubed, there are 0.4 moles. Well, if I only have half a decimeter cubed, so half that, I must have half the number of moles, so 0.2 moles of sodium chloride. So you might have noticed a pattern in those previous examples. We were often either multiplying or dividing, and that's because there is an equation that we can use and plug some numbers in to work this out. So that equation is concentration in moles per decimeter cubed is equal to moles divided by volume. Volume is always in decimeter cubed. However, even though that's the standard units, as chemists, we don't often work with litres of material. It's way too much liquid. So you are usually going to have to, not always, but usually have to do a unit conversion. Quite often, questions are given in centimetres cubed because that's a practical amount to work within a lab. So you will need to divide by 1,000 to turn that into decimeters cubed. If you find it easier to rearrange an equation with a triangle, I have shown that as well. In order to use a triangle to rearrange something, then you cover over what it is that you are interested in finding out, and then you read off the other 2 terms in terms of what to do. Okay, let's have a practice at using this equation now. So, in order to tackle this question, we actually need two equations. We need the one that we've just spoken about. Now, I abbreviate the concentration equation to N equals VC. N is the number of moles, V is volume in decimeters cubed, and C is concentration in moles per decimeter cubed. But if you look at those terms there, N, V, and C, we don't actually have enough information to go straight into using this equation, because look at the question. I'm given here a mass. So I need to use this mass in order to work out the moles. So moles is equal to mass divided by mR. So let's do this bit first of all. So we're going to work out the moles of sodium hydroxide. Our mass is 0.5 grams. Our MR, we're going to use our periodic table. So we have there 23 for 1 sodium plus 16 for 1 oxygen plus 1. And that gives us a total MR of 40. The number of moles therefore works out, stick it into your calculator, as 0.0125. Now let's come back to our concentration equation. We need to rearrange it so that it is concentration equals. Use the triangle on the previous slide, skip back a bit in the video if that's helpful. But we're dividing both sides by V. So N is equal to moles divided by volume. Now let's put what we know into this equation. So the moles we just worked out, 0.0125, divided by the volume. Now here is a really common place people get tripped up. So we forget quite often that this volume needs to be in decimeters cubed. So we have to take that 100 centimeters cubed and divide it by 1,000. Now brackets are your friend here. Don't try and put this fully into your calculator without actually breaking it up. So do 0.0125 divided by open brackets, 100 divided by 1,000, close brackets, then press equals, and it gets us our overall answer of 0.125 moles per decimeter cubed. So for this second example, it's a little bit different, because we are being asked to calculate the concentration in grams per decimeter cubed. It is a much less common unit of concentration because moles per decimeter cubed is a standard, but they can ask for it, you will come across it, and this is how we do it. We'll start with our normal concentration equation. So N is equal to VC. Moles is equal to volume times by concentration. Now we can actually work with this straight away because we have the moles and we have the volume. Let's rearrange it first though. So we're going to divide both sides by V, and that gets us to our rearranged form of concentration is equal to moles divided by volume. Now let's pop the numbers in. So our moles is 0.02 divided by the volume, which is 25. Convert that into decimeters cubed by dividing by 1,000. That gets us to a concentration of 0.8 moles per decimeter cubed. But we've now got another conversion to make. So we want to go from moles per decimeter cubed to grams per decimeter cubed. How do we convert from moles to mass? Because grams are the units for mass, right? Well, we need another equation. So we're going to use our moles equation. Moles is equal to mass divided by mR. We are trying to find the mass. We're trying to convert into grams. So let's rearrange this. Mass is equal to mR times the moles. And that's what we do. We have moles per decimeter cubed. We want to find the mass, grams per decimeter cubed. How do we get there, therefore? We times by the mR. So We are therefore going to take the 0.8 moles per decimeter cubed and times by the MR of the sodium hydroxide. So that's 23 plus 16 plus 1 is same as the previous question, so it's 40. And that gets us to our overall answer of 32 grams per decimeter cubed. There we go. Finally, let's cover how to not make silly mistakes, because we don't want to fully understand it, get so far with everything, and then make one of these mistakes and we've lost half our marks, all of our marks, etc. So, first one, don't forget to convert into standard units. That is common across all chemistry calculations. In our case that we've worked with today, we need our volumes in decimeters cubed. So easy to miss. You've got to usually be dividing by 1,000 to turn centimeters cubed into decimeters cubed. And mass is in grams. The next really common error that I see so often is making calculator errors. Let's not do that. So you need to make sure you use your calculator cleverly. Don't just bung the whole thing in one go and ask your calculator to be doing multiple steps. Use brackets, they are your friends. Break it up step by step. So do this times this, press equals, and then carry on using the answer into the next bit of the calculation. So don't make a calculator error. Break it down, keep it simple. And label the lines of your calculation. This is not maths. We don't just scatter number confetti around for examiners to magically pull out what it is that you know, because every number in chemistry has a meaning. It's a volume, it's a concentration, it's a mass, it's a moles, etc. So label each line of your calculation with what it is that that number means. Moles of hydrogen ions, concentration of sodium chloride, etc., etc. Thanks for watching, and if you found this helpful, then don't forget to hit like and subscribe now. I would love to help you do the best you can in your GCSE or A-level chemistry. So let's do the next video together now.